Professor Dimple Kumar, are you online?
Yes, I'm online. I just want somebody to. Can you hear me?
Yeah, yes, sir. Yes, sir. We can hear you.
Yes. Let me just share my screen.
So before we start, I would like to introduce you.
Yes, sir. Please go ahead.
Yeah. હવે પછીનું જે બે વ્યાખ્યાનો છે એમાં સૌથી પહેલું વ્યાખ્યાન ડોક્ટર ડિમ્પલ કુમાર એન્ડ 40,000 તેઓનું વ્યાખ્યાન આપણે સાંભળવાના છીએ. તેમના વિશે જો હું થોડુંક કહું તો ડોક્ટર ડિમ્પલ કુમાર 40,000 is a professor at Department of Applied Mathematics, Virginia Military Institute, Lexington, United States. He has completed his PhD at MS University of Baroda and has published more than 56 research papers in national and international reputed journals. Professor 40,000 has delivered more than 60 lectures in conferences and invited talks. He is a member of editorial board of 11 journals and he has reviewer of more than 25 research journals. Professor 40,000 has been awarded the Jackson Prize for Excellence in Published Scholarly Work, Jackson VMIRL Matthew Fountain Maury Prize for Excellence in Research, Wilbur S. Inman Jr. 26 Research Award, Natural Science and Mathematics, VMI Institute Ceremony VMI Granting Aid Summer Research Award, and Professor 40,000 has about 25 years of teaching experience at university level. So now stage is yours, Professor. You can go ahead. I'll just remind you before just 5 minutes of completion time.
Sure.
Please, sir.
Thank you so much for the invite. I appreciate Dr. Haribhai Khatharia, Dr. Udayan Prajapati for the invite, and the coordinates, Professor Ekta Sa and Professor Sejal Sa. Thanks, guys, for giving me the opportunity to share my thoughts with you. Can you see my screen, guys?
Yes, sir.
Yes.
Okay. So the extensive title of my talk is the exact controllability of nonlinear third order dispersion system. We are going to see the monotone operator theory. Very less literature is there based on the monotone operator theory. That's what we are going to see over here. And then after, I'm going to weaken the Lipschitz continuity by the method of integral contractor. And if time permits, I would like to say a little bit about the fixed point theory too. Outline of the talk is designed like this. First of all, I just would like to give you the introduction and the motivation of this problem and the existence and uniqueness of the solution operator W by 3 different ways. And then after, I will let you know how the controllability problem is to be reduced by the solvability problem. And then we'll go for our main control result based on the monotone operator theory. Then after, we will learn the new technique that is called the integral contractor, and we will try to prove the control result based on the integral contractor. And I hope probably the time will not permit us to go through the integral differential system. But if we have some time, I would like to give you a little bit hint about the integral differential KdV system and the control based on this one. Finally, I will give you the conclusion and the further investigation. If somebody is interested, then he can extend this work in different ways. This talk is completely based on the functional and real analysis. So those who have just finished their masters or those who are in the masters, they don't have to worry about this thing. I think everyone can understand this thing very easily. So we are not going to do any hi-fi things over here or more technical things over here. I was told by Dr. Khatharia that this is the Gujarat Ganit Mandal, and that's why talk should not be completely technical. So that's why very frequently we will be discussing something else than the technical matters. So first of all, this is just a title. First of all, let me let you know that what we mean by the control theory. In very layman sense, suppose we have one airplane moving the air and we have missile on the ground. So we can give the proper control to the missile so that it can hit the warplane in the exact place. You can see here the yellow spot. Suppose this is the point I have fixed. And if I want to hit this warplane at exactly this point with the help of this missile, that means I have to give the proper control to the missile so that it can hit the warplane in a proper time period, in given time period, and at the proper place. If your missile hits the warplane exactly at the same point, that is called the exact controllability. but you know that both are the moving objects, and that's why it is quite impossible or very hard, I would say, to achieve the exact controllability. But it may possible that your missile may hit this plane over here or here, somewhere in the neighboring of this point, whatever you have fixed. And that is called the approximate controllability. There are different notions of controllability like local controllability, then null controllability, then optimal controllability. If you Google my name and try to figure it out my papers, you will find all different types of control results in the literature. Without wasting time, I just would like to start with a problem. So the third order dispersion, actually the control problem that was first introduced by Kalman in, I would say in 1967. And then after subsequent work was done. I mean to say that it was in the finite dimension, linear system. Then after people started working in the nonlinear part, again in the finite dimension. In 19s, people started working in the infinite dimension. Now, guys, look at over here. If I say infinite dimension, please don't get disturbed. Let me just divert myself, because let me just share something with you guys. Before 13 years, when I came over here in the United States, and I was interviewed over here in one of the universities, and I was asked to present my work based on the teaching for half an hour. And I chose the article that is the infinite series. I know actually we learn English from Britishers, and that's why our pronunciation, they are very much similar to Britishers. But American pronunciation, they are different. And when I started my talk, I wrote it down infinite series. And I spoke this word so many times, number of times. After some times, you won't believe, but all the students and the staff members sitting on the last rows, they were just looking at me with a strange eyes. And I was wondering that why this happened. You won't believe, after the talk, one of the professor, Dr. Dewald, he came to me and he said that I do understand that opposition of finite is infinite. So you are right. But here in the United States, we speak infinite. So when I came over here at that time, I was just keeping my eyes open to learn the new technique, new rhythm of the language. And that's why probably then after I shared this thing with one of my professors, and you won't believe what he said, he said that that's why the Americans and Britishers, they are separated by the common language. So that happens. Anyway, let me just come to my point. So today we are going to talk about the exact controllability of the nonlinear third order dispersion system. And this is the system you can see over here, del W by del T plus del cube W by del X cube. This is third order. That's why it is called third order. GU is defined over here, GU of XT that is here. And this is a nonlinear term. This is the term what I have added over here. This is the term nonlinear term, because you know that most of the real life problem, they are nonlinear in nature. And in domain T greater than or equal to 0, 0 is less than or equal to X is less than or equal to 2 pi in the periodic boundary conditions with the initial condition. As I told you, operator G is defined in this form. And this Gx, this function G, capital G, that is the boundary linear operator, and G is a piecewise continuous non-negative function. So integral part of G that is defined like this, and my non-linear operator that is continuous in the domain. The motivation. Cortevas. This is called the KdV equation. Now, in 18th century, the aeroplane that was not investigated, that was not there. So people used to travel by the steamer. Cortevas, he was traveling in a steamer and he was on deck of the steamer and he was just looking at the water waves. So water waves, they were moving like this. An idea came to his mind that is it possible to make any mathematical formulation of these tides or water waves? And then after he discussed the same thing with De Vries, his friend, and finally they restricted their problem in a channel and they came to the conclusion that the model, they prepared the model for the propagation of some surface water waves along a channel in this form. This was the model they formed, mathematical formulation for the surface water waves. And what is this eta and then alpha and sigma? They are like this. Eta is a surface elevation about the equilibrium level L. Alpha is a small constant related to the uniform motion of the liquid. G is a gravitational constant, and sigma is equal to L cubed by 3 minus TL over rho G with the surface capillary tension T and the density rho. If you pose the same thing on the whole real line or on the periodic domain, the above equation with the help of some transformation can be reduced to this one. And that is nothing but the third order dispersion equation. So we are mainly related to this one, but the system, whatever they formulated, that was just a linear system. Here you can see that U is a function of two variables X and T, and the suffix denotes the partial derivatives. I don't say that KdV equation is extensively studied, but in terms of control, I don't think that it is extensively studied, because when this one was identified and then after first the control part, that was done by Russell and Zhang, and that's what I would like to discuss over here. Russell and Zhang, they just put the they derived the control part of this KdV equation. Then after again the problem remained unsolved for almost 15-20 years, and we proved the controllability of the nonlinear system of KdV equation. Another thing is control definition that is different from system to system. For this particular system, Russell and Zhang, they consider the control definition like this. Let t is greater than 0 be a given, and let g is a continuous function associated with capital G, whatever you have defined, and given initial final stage, whatever we have desired, if Wt in L2 with integral part of Wt is equal to 0, there exists a control U in L2 such that our system with initial and boundary condition satisfies the terminal condition Wxt equal to Wt in L2. Also, they have proved this norm of W is less than or equal to C1 and this norm condition. Our definition is slightly different because of that nonlinear portion. So definition for our system 1, 2, 3 nonlinear system, the system 1, 2, 3 is said to be controllable, or I would say exactly controllable. Whenever we are in the infinite dimension space, at that time we refer the exact controllability. If we are in the finite dimension space, the same thing can be referred as the simply total controllability or complete controllability. So system 1, 2, 3 is said to be exactly controllable over an interval 0 to t if for any final desired state Wt in L2 with integral part of Lt equal to 0, there exists control U. We define the Hilbert space over here x equal to L2 like this, such that the corresponding solution W of 1, 2, 3 satisfies Wxt equal to Wt. That means we need to define one operator, solution operator, I would say W, in terms of L2 to L2. So W from L2 to L2, we define like this, Wuxt equal to Wxt, where this Wxt is nothing but the same thing. That is the unique solution of the system corresponding to our control U. Please make sure that guys that you are working with two different space. One is your state space and another is your control space. So please keep in mind this thing. Now, existence and uniqueness of the solution operator W. So what we mean by the existence, because once you define your operator, you have to make sure about the existence and uniqueness of your solution operator. And for that, we have to define a domain of A, because this A, operator A, is a generator of your strongly continuous semigroup, or I would say, it depends on the system, strongly continuous group or group of isometry. Here I have defined my domain of A, that is collection of all W in Sobolev space H cube, such that this boundary condition is satisfied for k equal to 0, 1, and 2, such that this A is defined as negative del cube W over del x cube. And it is quite simple to prove that inner product of A W and W that is equal to 0. Because if you take the inner product of AW and W and if you use the integration by parts techniques, of course, for partial derivative, here 3 times, you are going to get this one. So if you send this one to other side, this one is achieved. Another thing is, as I told you, this A is nothing but the infinitesimal generator of a C0 group of isometry over here. And that is given by phi, and this phi is bounded. So there exists one constant m such that this phi is bounded. These are some assumptions which are very quite normal, which we assume. And now we are in a position to give the mild solution of our system 1, 2, 3 nonlinear KdV equation, nonlinear, and this solution, mild solution, that is given in the form of Wxt equal to integration 0 to t phi t minus s guxs and phi t minus s f of this one. As I told you guys that I would like to use over here the monotone operator theory. And that's why I want to define the operators for each of my terminologies. So let me usually Niemitzsky operator that is always related to your nonlinear function. Here f is my nonlinear function. So let me define this one as the Niemitzsky operator capital N. Then after I would like to define phi t minus s and f, that is my operator w, k. So this whole one is nothing but just operator kn. And this is my operator h, something like this. Look at over here. So h, k, and n, they are defined like this from x to x, such that this one. And if you plug these values over here, this operator forms over here, this equation 14, equivalently we can write in the form of the operator like this, w is equal to hu plus k and w. Once you have this one in the operator form, now we can start checking whether this operator form that exists and what's about the uniqueness. So that's what we are going to see in 3 different ways. You can prove just by using one way, but for curiosity or for master students, they can try some simple things, some simple calculations, and try to figure it out some different things too. Here, my first lemma based on this one. So now onwards, I'm going to say whether equation 14 means mild solution or equation 18, there is nothing but the operator form of my mild solution. So both are equivalent. My first lemma is if nonlinear function satisfies this strongly monotone and it satisfies the growth condition, in that case, solution operator W is well defined. And that is quite natural because ultimately I have to prove that my operator KW, inner product KWW, that is strictly monotone, and nonlinear operator, Niemitzsky operator N is strictly or strongly monotone. If I'm able to prove this one, that means this one is done. Again, master students or those who have just finished your masters or those who are doing some MPhil or like this, they can prove this one very easily. I can give the hint over here. If I define HT equal to phi of T minus SWS, and this HT that is in the domain of A, and phi is nothing but the strongly continuous group of isometry. So naturally, I can go for the derivative of this operator. Once you have the derivative, that means you are getting this one. So send this one to other side, you are getting WT equal to H dash T minus AHT. And then plug this value over here for W. So KW and W, and after some calculations, you're going to get that is greater than or equal to 0. So that's not a big deal. And same way, we can have over here the Niemitzsky operator. Niemitzsky operator, after some calculations, just plug the values, you're going to get that is greater than or equal to negative beta W minus V squared. So L2 norm. So that is a strongly monotone. Once we have proved this one, that means we are done. We get the existence and uniqueness of the solution operator W. Second lemma that is based on the Lipschitz continuity. Most of the control paper, I'm going to say that almost all control paper, they are based on the Lipschitz continuity of the nonlinear operator F. And that's what I have done over here too. But later on, we are going to drop this condition. We are going to weaken this condition. That's what we are going to see after 10-15 minutes. So if my nonlinear operator F is Lipschitz continuous with some Lipschitz constant alpha, then also we can get that W is well defined and continuous. Once F is Lipschitz continuous, so naturally Kn, my operator Kn is also a contraction for sufficiently large n, and therefore by generalized contraction principle, we can say that equation 14 or 18 has the unique solution for each control U, and that proves the lemma. Third way of proving the existence and uniqueness, that is, now I would like to use the definition of subgradient. That is not derivative. Guys, please keep in mind there's a weaker notion of derivative. I didn't say that my nonlinear operator F is differentiable. So look at over here. Subgradient definition is something like this. Subgradient d of fx of f at point x, that is given like this. X lies in the ball with center 0 and radius r. And it is defined as d of fx collection of all p in R such that limit infimum of this part is greater than or equal to 0. And the same way we can prove the second subgradient. So d square of fx, that is the collection of all p from this set now, d of fx such that limit infimum of this one is greater than negative infinity. Using this one, I just would like to go for the next part. So suppose that for any r greater than 0, the second subgradient that is less than or equal to alpha, and second subgradient does exist. Value of the function at x0 is finite, and f satisfies the growth condition. Thanks to Rutherford and Walter, they said that if these first two conditions are satisfied, in that case, you can say that your nonlinear operator F is Lipschitz continuous. Once it is Lipschitz continuous, things are quite simple. And because of the local Lipschitz continuity, there exists unique solution for our equation 14 or 18 in the maximum interval 0 to T max, where T max is less than or equal to T. You cannot take T max is strictly less than T because Tanabe, he proved this theorem. If it is strictly less than T, then that is infinity. So that is not possible. So that's why, thanks to Tanabe, that it has to be less than or equal to T. And then the existence and uniqueness of the solution that is in the interval 0 to T can be obtained just by using the Grunwald's inequality and my growth condition. So this way, solution operator W is well defined. So you can use different ways. Just for the curiosity, I proved this. I used these three different ways, but technically it is not required. You can just go through one way and then after you can proceed further. Second part, that is again for the master students or recently those who have finished their masters and those who want to make the academic career. This is the homework for you guys. As I told you that I have used over here that second subgradient method. I didn't say that it is f is differentiable, but suppose f is differentiable, then my subgradient will be converted to the derivative. Nothing to be proved. As I say that f satisfies the growth condition, and you know that w is defined in terms of the nonlinear function f. So naturally, I can claim that W also satisfies the growth condition. Very simple thing. The C1 and C2 can be, that's a constant, can be measured in terms of these constants. I think this is the good exercise for the people, those who want to start their career in mathematics. Again, same thing. I said that F satisfies the Lipschitz continuity. Similarly, we can prove that W also satisfies the Lipschitz continuity with some Lipschitz constant, C3 like this. So now I would like to convert my controllability problem to solvability problem. This is the main thing. This paper was that was published before, I think 2-3 years back in Journal of Mathematical Analysis and Application Elsewhere, California. So if somebody is interested, he or she can go through this paper. Here I have defined one space x1 that is equal to collection of all x in L2 such that integral part of xt that is equal to integration 0 to 2 pi xt dt equal to 0. And I said that this x1 is a Hilbert space. I just wrote it down this thing in the paper, and you won't believe when I got the referee comments at that time, one of the referees, he asked me to prove this thing. I said it's very, I thought it's very easy to prove this thing, but when I tried to prove this thing, it took more than 8 to 10 days for me just to prove that x1 is a Hilbert space. Yes, guys, sometimes things are looking really very simple, but if you start working on it, you will realize this thing that things are always not that good. Sorry. Let's first define the operator L as a linear operator because this is the operator taken by Russell and Zheng. So I just adopted the same thing. And then after I used the technique used by Russell and Zheng, actually David Russell, he was my postdoc guide in Virginia Tech. I worked with him almost for 1 year. So Russell and Zheng, they proved this one. And based on this one, on that paper, we can write the WT, final desired state WT, that is equal to operator LU. I want to add my nonlinear operator over here too, but that's not, you cannot do anything randomly. See, in mathematics, once you state something, that means you have to have an evidence in support of a statement. So I have to have some concrete proof based on this one. That means I am looking for, see, for linear system ontoness, that is very simple. That's what proved by Russell and Zheng. But I want to prove the ontoness of my operator for the nonlinear portion, nonlinear operator. And that's why I cannot write like this. That's why what I'm going to do, I'm taking the decomposition of my space X as null space NL direct sum NL part. So I am looking for here NL null space is OK, but NL part you have to be very careful because we are looking for the inverse of the operator L, not in the full space, but the restricted space. So L has that is defined over here on NL part such that X1, not over here X1 to X, but in the NL part, as I told you, the restricted space such that L has that is the identity operator, L has L, there is the orthogonal projection of X onto NL part, and L has L that is equal to identity over NL part. And once you get, so one can obtain the unique nu in this NL part, unique nu NL part such that L nu equal to WT. And if we find such nu, in that case, we can get any control U also in X such that LU equal to WT. So just you can replace this nu by particularly U. Now I want to define the operator F for my nonlinear part. So my nonlinear operator F is defined in this one, X to X1. Because of the definition of L, then F and ontoness of L, we can say that this map F is well defined. First of all, whenever you define your map, make sure that it should be well defined. And now system 1, 2, 3 is exactly controllable if for every WT in X1 there exists the solution control U in X such that WT is equal to LU plus FU. Now I am in a position to write it down LU plus FU. So if I take L has both the sides, I am getting L has WT equal to this one. This is just U, but I can replace in general this U by nu. So mainly I'm concerned about this part, L has F nu. But all this discussion, why we are doing this thing, all this discussion that lead us to this very important lemma that suppose that the equation has a solution nu for every WT in X1, the system is exactly controllable. And that's what we are going to use for our main result. So suppose that nonlinear function f satisfies the Lipschitz continuity with sufficiently small Lipschitz constant alpha, then the nonlinear system 1, 2, 3 is exactly controllable. As you know that W is well defined and Lipschitz continuous. Because W is well defined, you can see again my operator f. Look at W and f. So f is defined in terms of W. Once W is Lipschitz continuous, so f, and that's why you can say capital F2. Again, small proof, 4 lines proof are there. So I think one can prove that one very easily. So because W is well defined and Lipschitz continuous, so that we can say that my operator f is also Lipschitz continuous and in this form. And thus, since L has is a bounded linear operator, we observe that L has f is a contraction for alpha sufficiently large for this one. So you can cancel this m, alpha, all these terminologies over here, and you can get the contraction over here. And that's why based on the contraction principle, we can say that we can get the exact controllability of the system. Third part, suppose my f satisfies strongly monotone and growth conditions. Nonlinear function f satisfies these two conditions. Main thing is here I have dropped this condition. Guys, whenever you are doing research at that time, please be ready with the hurdles, some obstacles. It will come to your way, but don't try to give up. When I was doing my research, actually I finished my research, but I started my research with my first student, and at the same time we faced one big problem. Big problem I mean to say that whenever, if you look at from 1987 to 2008 or 2010, almost every paper you will find the assumptions of the compactness of the semi-group or the group. But in 2008, Dr. Hernandez from Ireland, he figured it out that if you are working with the compactness assumptions of the semi-group, that means you are no longer working in the infinite dimension space, but you are falling to the finite dimension space. And that result was proved by one of the professors over here in University of Virginia, Dr. Trigiani. And Lassika Trigiani, she is extremely good. She wrote 2 books based on partial differential equation. And even today, IIT people, they are using that books. So her husband, Dr. Trigiani, I got the opportunity to meet these guys, and we had a good discussion too. So he proved this result in long back in 1989 or like this, but people just ignore that part. But then after people noticed this thing in 2008 or 2009, that compactness assumptions that is not valid in the infinite dimension space. And that was the big hurdles. And you won't believe most of the control theories, they diverted, or some of them they dropped also. They just stopped working in the field. So don't give up, guys. I just took this one as the challenge. And my first student, we proved the whole thesis that is based on this one, that we remove the compactness assumptions using by some functional and real analysis techniques. So here I said that f is compact. So please keep in mind this thing, f is compact. That doesn't mean that I am talking about this f is compact. But that does not mean that my semi-group or my group is compact. It is closed. Here it is compact, as small f is compact. So I just use the technique that closed image of a compact set is compact. And that's the reason I have just assumed over here that f is compact. If you want to drop this one, that's fine, because already we proved the existence, I mean to say exact controllability. This is another way of approaching the exact controllability of the given KdV equation. So I define the operator R from NL part to NL part such that R nu equal to nu plus L has F and L has F nu. If you take the inner product, you are going to get this one. Mainly we are concerned about this one, L has of FQ. And because my F satisfies the growth condition, look at over here, F2, naturally this F nu satisfies the growth condition. So if you take this inner product by Cauchy-Schwarz inequality, you're going to get this one. If you plug this value back over here in this inner product, R u nu and nu here, that means you're going to get this one. But why we are doing this thing? See, again, limit norm of nu tends to infinity, and we are getting norm inner product of R nu over norm of nu equal to infinity. This is nothing but the coercivity of the operator R. I want to use now mainly monotone operator portion over here. This is the coercive operator. My capital F is compact. That means L has F is compact. That means R is the thing, but this operator R is nothing but the compact perturbation of a strongly monotone operator. Compact perturbation of a strongly monotone operator along with the coercivity will always give you the definition of type M. For all this definition, you can refer the book of Joshi and Bose. They both were the professors in IIT Bombay. Dr. Joshi, he retired in 2005, I think so. MC Joshi, he retired in 2005. And Bose, actually, they wrote down one book based on the monotone operator theory. You don't find more than 3 or 4 books based on monotone operator theory. Very little literature is there. And this book probably right now it is not even available. But it's a fantastic book. I went through this book 3-4 times. Fantastic book. So all the definitions are given over here. And once you are of type M, that means it is that operator is always onto. That's what they have proved. Theorem chapter 3, article 6, theorem 9. They have proved this one, both these guys, thanks to them, that R is onto. Once we are getting onto map, that means we are achieving the exact controllability. So that's why I told you that I have proved the result using the monotone operator theory. Okay, guys. Now, I just would like to weaken the method of integral contractor. Guys, at this stage, again, I just would like to share my thoughts with you guys. Let me just divert a little bit. There are different ways of proving the results, doing research. So don't try to criticize anybody, please. Everyone is doing by its own the best, whatever he or she can do. So I have seen so many times that some people are criticizing, other people don't do this thing. Please, guys, everyone is doing at his or her level best. Let me give you one quote right now. I would say that Benjamin Franklin, one day he said this thing that if you are really working hard and if you are honest to your work and if people are not criticizing you, that means you are doing something wrong. See here. So if you are honest, if you are working hard, hurdles will be there in your life, but always try to convert that thing for your growth, for your positivity. Don't try to involve in any type of rubbish things that will stop your progress. So if you want to progress in your field, just avoid the negative part and always try to think in a positive way. And that you are not obliging somebody by doing these things. You are obliging yourself, because in that case, you can completely focus on your work and you can do amazing things in your life. Please trust me, guys. That's my experience too. Anyway, guys, so let me again come to my topic, that method of integral contractor. For that, I need to define one space. Let C be a space of all continuous functions from the interval to L2. That denotes the Banach space of continuous functions in J with this subnorm, and define the solution operator W from X to C by WUT equal to WXT. Where WXT is a unique solution of the nonlinear integral equation, 14 or 18, whatever you want to say. So this is the space, and I want to use this space to define the method of integral contractor. So this is what I mean by the integral contractor. Suppose operator gamma from J cross L2 to bounded continuous operator on C, and there exists a positive constant gamma such that supremum of norm of this norm completes over here less than or equal to gamma norm of Y at C. Then we say that F has a bounded integral contractor I with respect to our semigroup or group phi. Why I said that this one is a weaker condition of Lipschitz continuity. Suppose I take gamma equal to 0. If you take gamma equal to 0, this will be gone. This will be gone. This part will be gone. What is left out? F of t wt plus yt minus f of t wt, that is less than or equal to gamma. What is this? That is nothing but the Lipschitz continuity. Look at what here. So that is a Lipschitz continuity. So if you say that A implies B, that means your A is a very strong condition, B is weaker than A. So here exactly same over here. Lipschitz continuity implies this method of integral contractor, but the converse is not true. So it's a weaker notion. I faced one problem when I was working with this integral contractor method. It gives me the existence of my solution operator W, but it did not provide me the uniqueness. And that's why we define the another definition, and that is called the regularity of the integral contractor. The regularity along with the integral contractor gives us the existence and uniqueness. Sorry. A bounded integral contractor gamma is said to be regular if the integral equation yt plus integration 0 to t phi t minus s is equal to zt has a solution y in C for every w and z in C. Yes, yes, guys, in United States, we say this one as Z, not Z. So please pardon me. Please try to cooperate me. OK, and as I told you that Lipschitz continuity implies integral contractor, but converse is not true. Now, again, let's go back. I'm going to say go for our main theorem. Suppose that our integral contractor condition is satisfied, means our nonlinear operator f satisfies the integral contractor as well as the regularity. Then the solution operator w, because you know that this f is defined in terms of w and this f, that means capital F, is defined in terms of f. So f is an integral contractor, then we have proved that w is also w is a Lipschitz continuous. It's a long proof. 2-page proof is there. I just omitted the proof over here. So if you are interested, please try to refer this paper. You will find the whole proof. So it's not that easy. It looks very easy, but it's not that easy. It's a long proof. So W is Lipschitz continuous. Once you have W Lipschitz continuous, then after things are really very simple to prove the exact controllability using the integral contractor. So suppose that the nonlinear operator f is a regular bounded integral contractor I, and gamma, whatever we have defined in the definition of integral contractor, is sufficiently small, then the nonlinear system 1, 2, 3 is exactly controllable on my space x1. So just by this theorem 4, just by this using this theorem 4, we can say that the solution operator W is well defined and Lipschitz continuous. That's why W is integral contractor. That's why capital F is integral contractor, because capital F is defined in terms of small f and w. And if you write L has, so naturally, if this condition is satisfied, then our equation L has 32 has a unique solution using the contraction principle, and we can have the exact controllability by using the contraction method. So here I have proved, as I told you, that integral contractor method and the regularity, and I'm dropping the condition of Lipschitz continuity. You will not find any literature based on this one except this paper. Any literature you will not find, any paper, I mean, it's a research article. So this is the open problem. You can add, you can drop down the condition of Lipschitz continuity in your other control problems too, in your fractional order problems too, in your stochastic problems too. Everywhere you can do this thing, and you can have plenty of papers. And that will be published in good journals. Trust me, guys. I have now last 10 minutes left out. So let me just give you just brief idea about the integral differential KdV equation. This is the integral differential KdV equation. So now I'm not just working with my nonlinear term, but it's an integral differential nonlinear operator. And my rest of the things are exactly same. Look at over here, G, G1, everything is defined. Operator A is defined like this, exactly same. Only thing is now my definition of control will be a little bit different. So system 1, 2, 3 is said to be controllable over J if for every W1 in X1, you know this thing, with WT equal to 0, there exists a control U in L2 such that the corresponding solution WXT of 1, 2, 3, system 1, 2, 3 satisfies WB equal to X1. Here we are going to see the Schaffer, I use the Schaffer fixed point theorem. Schaffer fixed point theorem, it says that let F be a normal linear space and map F is defined like this. E2 is be a completely continuous operator. First thing, guys, why we require completely continuous operator? Or other way around, I have to prove that my nonlinear operator F is completely continuous. Why complete continuity? Again, those who are expert in the field, they know it very well. But for the initial stage students, MSc students, as well as those who have started their career, complete continuity, actually what we are looking for. You know that compactness implies closed and bounded, and closed and bounded implies compactness in the finite dimension space. But for the infinite dimensional space, compactness implies closed and bounded. But the reverse is not true. That means you cannot say that your operator is closed as well as bounded, and you can achieve the compactness of that operator. No, that's not possible. But thanks to Arzela and Ascoli, they have proved this thing that if in infinite dimension space, if your nonlinear operator F is uniformly bounded and equicontinuous, very strong notion of continuity. uniformly bounded and equicontinuous, in that case, you can achieve the compactness of the operator. So that's what that's tool I have used over here. Yes.
You still have 5 minutes, sir.
Okay, sure. Thank you. I'll be concluding in 5 minutes. Yeah. So we have some assumptions over here, and G satisfies the characteristic condition. So that is okay. Characteristic condition, that means function is measurable with respect to first variable and continuous with respect to second variable. We have some conditions over here, and this is the mild solution of the system. And then after we have mild solution of the system that is given like this. For this particular problem, I have defined my control like this, and I just plug the value of the control in my mild solution with the help of the operator. And then after I work with the operator. Then after I use some real analysis technique over here, try to figure it out, the exact controllability of integral differential KdV equation without compactness assumptions. And this paper is also published in Journal of Mathematical Analysis and Application elsewhere. So let me just keep the proof and let's go for the conclusion, because we are almost at the end. This is just the proof of this one. As I told you, my nonlinear operator F is uniformly bounded as well as the equicontinuous, and therefore it is compact. And therefore we can use the theorem, I mean to say, Schaffer fixed point theorem. So what we have done in this 45 minutes, Russell and Zhang proved the controllability result only for the linear system. We have proved for the nonlinear system. We have given 3 different ways of proving the solution operator W. Lipschitz continuity is weakened by the method of integral contractor and regularity. And we proved the controllability result. Assumptions of the compactness of the semi-group has been dropped, and we prove the control result. What we can do next? The further investigation. If somebody is interested, just look at over here. I just used the monotone operator theory over here, but if you look at the literature, you can find lots of things based on de Vries equation, KdV equation, and you can directly prove the control result of KdV equation. Parabolic equation too. By defining Niemitzsky operator for integral differential nonlinear function, one can extend the result in a similar way. KdV equation 1, 2, 3 can be extended to finite and infinite time and state dependent delay. Guys, time dependent and state dependent, this is really very important things. Whenever you want to work in the infinite dimension space with delay term, at that time you are not allowed to work in a full space. You have to restrict your space, and I have generated one space that is called the pseudo phase space, and you can find the definition based on this one. That paper was published in JOTA in 2012. So I don't have time. Otherwise, sometimes we will discuss about this delay system too. An appropriate definition of the phase space will lead us to the controllability result. Fractional order KdV equation, that is also important. I will give you the glimpse of this fractional order, what we mean by fractional order, and one can go for the numerical approach of the computational control, and we can find the graph, and that is also interesting and useful. The fractional order system that is like this. Del to the power alpha lies between 0 and 1. And we can find here you cannot work with the differentiability of the operator F, but you need to go through the Riemann-Liouville derivative or Caputo derivative. Caputo, because derivative of the constant in terms of Caputo derivative, that is 0, but for Riemann-Liouville, that is not 0. So go for Caputo derivative and you can get the solution. These are some references I have used over here. At this stage, my last remark is when I was doing, again, let me just divert a little bit. When I was doing my MPhil at that time, my professor, he told me one thing. So always keep your eyes open, guys. And if somebody gives you some good hint, some good advice, it should be in your mind forever. That's what I've been doing since last 25 years. He told me this thing that, Dimple, now you have finished your MPhil and maybe you will be in the field of mathematics. You will be teaching to your students. Always try to say, that was his words, still I remember, Zil ke us par. If you are only discussing the things given in the book, people will not be interested. So always try to give the people, I mean to say students, something beyond the scope of the book. So people will be interested in your class. And thanks to him that I got lots of things, lots of good things by the grace of God. I was so fortunate that I got good professors in my life and I got good guidance from them too. Actually, you know, guys, the education is always brings the responsibility. Once you are educated, once you have done PhD and you are holding some good position, it is very much, you are so many responsible to the society, You are responsible to the mathematical community. So please, guys, don't try to give up. Try your best and make your mathematical community healthy. Thank you so much, guys. These are some references, and I would like to request the organizers. These are the papers. If you want to refer, I would like to request the organizer, if it is possible, try to send this link to me so that I can upload this link to my YouTube channel. So you guys can refer this one. If somebody is interested, you guys can refer this thing anytime. Thank you so much again for giving me the opportunity to share my thoughts with you. Thanks for the invite. I appreciate. Thank you.
Thank you very much, sir. It was a really wonderful lecture. And our participants, especially those who are working in this field, this area, which definitely they will be benefited by the content which you have presented here.
Thank you. My pleasure.
Any questions, anyone? Any participant, you have any questions you want to ask to sir? Okay, sir. So thank you very much. It was a really nice lecture.
Thank you so much. Thank you.
Thank you very much.
Mm-hmm.